Okay, here's a last-minute high-level physics final review to help you study for tomorrow's exam. This goes for all questions, whether it's a constructed response or a multiple choice question. Read the questions through 3 times. Read the question through once, then the second time, read and underline, box things, whatever you need to do. Think about, and then the third time, think about any information you get from the reference sheet. Okay, so an electron is located in an electric field of magnitude 600 newtons per coulomb. What is the magnitude of the electrostatic force acting on the electron? I've read it through once. I haven't underlined or done anything else. Now I'm going back through. An electron is located in an electric field of magnitude 600 newtons per coulomb. I'm going to box this part information up. What is the magnitude of the electrostatic force? That's what I'm looking for, acting on the electron. Okay, I only have 2 pieces of information. Usually I need 3 pieces of information. Okay, a couple of things you can do. If you notice it, the electron is giving you more information. But you could also go to your reference sheet right now, too, and think about what formula you're going to use before you think about that last piece of information. Okay? Take this electrostatic force. You go to the right-hand side of your reference table, and we're going to electricity because we see the word electric. That means we go to the electricity section of the reference table. We go down here, we see electrostatic force, and we go to the left-hand side. Okay, this equation has f of e, but I scroll down. I see another f of e, but I scroll down and that's it. The first 2 equations are the only ones with f of e in them. Okay. Okay, now I also have this electric field of magnitude. I look down here. Okay, electric field, that could be right. Keep going down. Keep going down. Okay, there's nothing else like that, so electric field must be it. So I also have an E. Is there an E in the first equation? No, but there's an E in the second one. So I know I have E, and I know I'm looking for f of e. I also need to have, they must have given me Q, because I can only solve for one unknown. What do we know about an electron? We know that an electron has 1.6 times 10 to the negative 19th coulombs of charge. It's on the front of the reference table. It has that 1 E. So, and if I were to cross multiply, I would get f of e equals e times q, so 600 times 1.6 times 10 to the negative 19th gets me 9.6 times 10 to the negative 17th, and I get that answer. Do you see how even if you didn't have much answer, I can use my reference sheet to find these information, okay? And think about what you don't know, but in this information. Okay, scalar versus vector. Vectors have both direction and magnitude. So velocity, displacement, force, momentum, and acceleration. Those are your biggest ones. Scalars just have magnitude, no direction. Speed, doesn't matter what direction I'm going in. My speed doesn't matter direction, neither does distance. Mass and time, I can't have a negative time or a negative mass. They only have one thing. Energy is also a scalar. The only weird thing is your energy charts, energy diagrams, which can have a negative number. But energy is a scalar quantity. Okay, so when we talk about drawings, we are always going to measure with a centimeter side of the ruler, but they must be set up in this formation. See how this one goes tip to tail and goes there. They must be laid out tip to the tail of the next one. Then the resultant can be drawn from the end of one to the tip of the other. If they are not in that tip to tail formation, you will have to move it. Here, they are located tail to tail. See how the tail of both arrowheads are connected. So this one, you need to move this up here to get them in the tip to tail formation. And then you can draw in your resultant. Okay, and you're going to measure with a ruler in centimeters to get your scale, and then measure this to convert back to your scale. Okay, when we talk about these equations, we call them the big 5 because they're all sort of connected, except that this one is the big difference one. This first one above the line is the only one without an acceleration. It deals with when you're constant velocity. You have balanced forces, you're at constant velocity. This is when you use this a lot when you're in horizontal projectile motion. These are used when you're in free fall. We have a constant acceleration in free fall. Gravity is our acceleration. So velocity is always changing here, but acceleration stays constant. The big thing is knowing what's different. This one has no A. This one has no D. They both have initial velocity and final velocity, acceleration and time, but no distance. This one has a distance, initial velocity, time, and acceleration, but no final velocity. And this last one has final velocity, initial velocity, acceleration, and distance, but no time. So you use the equation with what you know, because we can't solve an equation when we have two unknowns. Vertical projectile motion. So the big thing here is that my velocity is going up. My acceleration is going down. So this is where it's important to use that negative 9.81 because the velocity and the acceleration are going in opposite directions. At the peak here, we know the final velocity is 0. So the time to peak is that time. The time for round trip is twice that time. So if they give it to you at an angle, a certain velocity shifted at an angle, you're going to have to break it out into its components. And then once you have it into components, then it's just like doing a vertical. You find the time to the peak. Remember though, everything on this side is the same as on that side. And the motion in the horizontal direction is just a constant velocity. The time is just controlled in the vertical direction. Here, you may think you have an initial velocity, but that initial velocity is only in the horizontal direction, not in the vertical direction. The initial speed in the vertical direction is 0 meters per second. Okay? And if you use a negative acceleration, you have to also use a negative distance so that you don't get only one negative number under the square root and get an error message. Okay, circular motion. So even though it's driving it at a constant speed, the velocity is constantly changing because the direction is changing. The acceleration is a squared. The acceleration is v squared over r. This is when it's a radius, the distance from the center to the outside. The acceleration is always pointing inward. The force is also pointing inward. The velocity is tangential to the movement. This one would be going in a clockwise direction. Newton's first law. This one is really an object wants to stay in rest or stay in constant straight line motion. But the big thing to remember from this law is inertia. The more mass something has, the more inertia something has. Newton's second law, an unbalanced force causes a body to accelerate. So if this is some number, say 10, then this also has to be a number. Acceleration can't be 0 if this is a number. But if this is 0, this also has to be 0. Okay? So if this is, and when we have an unbalanced force, that means this is not 0. And we look at these in the planes, in separate planes. So first let's look in the vertical direction. We have our normal force pushing off the ground, and it is equal and opposite to our weight. The weight is equal to F of G, which is equal to mass times gravity. Remember, mass and weight are not the same things. Mass stays the same on any planet, the moon, wherever I am. Weight depends on the force of gravity. And the normal force is the opposite one. Here, we usually call the applied force what it's pulling, and the friction force is what's preventing motion. It moves in the opposite direction of the velocity. And here we have a net force of 10 newtons to the right, so it would be accelerating to the right. Newton's third law. For every action, there's an equal and opposite reaction. So if I push against the wall with 100 newtons of force, the wall is going to push back with 100 newtons also. Later on, if I get mad and I just get frustrated, I push against the wall with 200 newtons of force, the wall will push back with 200 newtons. It's an equal and opposite reaction. Momentum is the tendency for an object to stay in motion. It's just sort of it combines the mass and the velocity. The more velocity it has, the faster something's going, the more it takes to stop. The more mass something has, the more it prevents. The idea of inertia, the more it doesn't want to stop.
Think about it. You get that big bullet, like a giant like ball moving, it doesn't want to stop. It is also a vector quantity, and it moves in the direction of the velocity. And the unit is just the kilogram times the meters per second. Impulse is the change in momentum, the time for the force to act, and it can also be a Newton times second. It's the same fine unit. So conservation of momentum. In a closed system, and that's all we deal with, the total momentum before is the same as the total momentum after the collision. So this is just showing a elastic collision. The biggest thing about this is making sure, like, this is all moving in the same direction, but if I have cars moving in opposite directions, being careful about the sign that left is negative and right is positive for speed, for velocity. There's three types of collisions. We have the elastic collision, and that's what was just sort of shown. Two objects collide and go in opposite directions before and after impact. Inelastic, two objects collide and are connected after impact, travel together as one after. An explosion, one object before and two objects after that travel in opposite directions. Okay, now on to waves. So this is our longitudinal wave. An example is sound. It requires a medium. It needs particles in the air, like particles, to bang together. So that particles in the air work to bang together to move the energy. Energy and motion are in the same direction. This is your transverse wave. Light, electromagnetic, ocean. The transverse waves can travel through a vacuum. Energy and motion are in perpendicular, so this motion is up and down, but the wave is moving, the energy is moving to the right, or the left and right, to the right. Wavelength can be measured from the crest to crest, can be measured from the end, from the beginning of one trough to the end of a crest, or it can be measured from the beginning of a crest to the end of a trough. It doesn't matter as long as you do one complete cycle. So from up a crest and down a trough. You have to think about a wave as like a day. You have to have both the daylight hours and the nighttime in a complete 24-hour cycle. So, and the wavelength is the distance to complete a wave. Amplitude is only measured from the equilibrium position to the top of the crest or the trough, but it's only measured from equilibrium up, not from crest to trough. The higher the amplitude, the louder it will be, the more energy the wave will have. Frequency is the number of cycles per second. This is something you've got to memorize. It definitely it comes up. It is one thing to memorize. Higher frequency, higher pitch. Period is the number of seconds per cycle. For the cycle, it is the time for one complete cycle. So where wavelength is measured in meters, period is measured in time, and it's the time to complete one cycle. Frequency and period are inverses of each other, and this one is on your reference sheet. That's that one, that formula. There are two constants on your reference table. The speed of sound is 331 meters per second. Usually when they call for that, it's going to say speed of sound at STP. STP means standard temperature and pressure, but that STP is signaling for you to go to the front of the reference sheet. Speed of light is 3 times 10 to the 8th meters per second. All electromagnetic waves travel at that, whether it's a gamma ray, a radio wave, a light wave, they all travel at the speed of light. The standard wave speed equals frequency times wavelength. That's the standard equation for a wave. But if they tell you a wave travels a certain distance and time, you can also use V equals your constant velocity formula, V equals D over T. And that can get you the speed of the wave also. Okay, when drawing a wave, so for example, a wavelength of 4 meters and an amplitude of 3 meters. The big thing is to make sure you label up your boxes. So you just give a scale. The other thing is a wavelength of 4 meters means that it is going to cross the this equilibrium line twice. It's going to have 2 dots by 4 meters. So we're going to have 2 dots, 2 and 4. And then you put in your amplitudes, okay? And then you just connect the dots. And it doesn't matter how perfect your drawing is. And I actually purposely made it messy so you can realize, but those dots, when you put them in first, show that you know where they need to be originally, okay? The big thing is it does cross halfway between at the halfway mark of the wavelength. If they say to draw one cycle, that's good. If this one was to draw two, you would have to repeat. You'd have to do another set. Okay, so be careful what they're telling you in the question. Phase. The two big ones are the big one is 180. So here, and here is 180 and halfway across. And that's when really something's 180 degrees is out of phase. Is usually when destructive interference happens. Maximum destructive interference is, and this is when your nodes happen. That's when you have the lowest point. It happens at the equilibrium. You have them at the equilibrium. You always have one more node than antinode, but don't forget to count at the walls too. Antinodes are maximum constructive interference, and you're only going to count the solid line, not the dashed reflection. Okay, so this is only the real line. Constructive interference is when two waves combine to result in a wave that's bigger than it started. It gets further away from the equilibrium line. So this wave is taller than these two waves. Destructive interference, the wave gets smaller. It gets closer to this equilibrium line. This is complete destructive, but as long as it's closer to this equilibrium line, that is destructive interference. And this generally happens when it's 180 degrees out of phase. See how these waves are opposite of the other waves? They're 180 degrees out of phase. The Doppler effect. So when an object moves towards you, think about when you're hearing a siren, what happens to the pitch? It gets, as it comes closer to you, you do hear it get louder, but the pitch is getting higher, okay? And that higher frequency, that higher pitch means it's a higher frequency and the wavelength is decreasing. And then when the object passes you, the wavelength increases and the frequency decreases, and then you hear the lower pitch. Diffraction is bending a wave around an obstacle. Allow sound to bend around a corner. The greater the wavelength, the more the diffraction. So the greater this wavelength coming in, the more it's going to diffract. Polarization. It's the separation of light waves into a single plane. Only applies to transverse waves, and sound waves cannot be polarized because they're longitudinal waves. Think about sunglasses. Resonance, and this is when you see this word vibrating, this is when you're starting to think resonance and two objects. When one object vibrating at a natural frequency causes a second object to into vibrational motion. So you're looking for one object causing movement of another without usually touching, or words like vibrations causing vibrations. The vibration is usually the words that set off resonance. Okay, law of reflection. So the angle of incidence is equal to the angle of reflection. Really important that you're only measuring off the normal line. The normal line is perpendicular to your surface. You measure the angle here and here, not here and here. It's only off the normal line. So make sure the base of your protractor is lined up with the normal line. There's two types of regular reflection, regular reflection and diffuse reflection. Regular reflection is what happens in a mirror. To smooth surface, rays reflect parallel, and we can see them because the rays stay parallel. The law of reflection applies. On a rough surface, the reflected rays are not parallel when they come off, but because of the uneven surface, they bounce and they scatter. But the law of reflection holds for each ray still. Refraction. When an EM ray changes speed at the boundary of two mediums, there's a change in speed, direction, wavelength, but the frequency remains the same. Otherwise, we'd have a lot of problems with all our signals as they come through glass. So theta I equals theta R in the law of reflection, because the speed of the wave stays constant. It's not changing mediums. It's in the same medium the entire time. In refraction, it's switching mediums. Going from a more dense to a less dense medium, you are going to have the angle of incidence is going to be less than the angle of, this angle is less than this angle. The speed of the wave increases in the second medium. It's fast, it's easier to drive, it's gonna go faster in air than it does in glass. And going from a less dense material, like going from air into water, the angle is going to get smaller and it's going to slow down. Okay, when we're talking about potential, kinetic, and total energy, most of the time it's going to be in a frictionless system. So the total energy is going to remain constant in the entire system. So here, when you find the potential energy is the same as the total energy. So the kinetic energy at the bottom is the same as that because the energy in total is going to stay the same. Here, then you know the total energy is the same because that's not going to change. You'd be able to find the potential energy here because you have the height. The energy total is the potential the energy total. The kinetic energy is equal to the energy total minus the potential energy. Energy transformation. So that was showing the potential gravitational to kinetic energy, and it going back and forth as it goes over a roller coaster. The other one that's common sometimes is the potential energy of a spring into kinetic energy. And you just use the spring formula. If they say there's energy lost to things that it can be lost to are heat, sound, friction. Okay. So as we said, there's two sides to work in electricity. So it's a matter of what they have in your formula. If you're dealing with circuits, you're going to be on the electricity side. If you're dealing with work and you are climbing a mountain or you're moving objects, it's going to be on the mechanic side. But the unit is the same. It's joules for all of work and energy. Power is watts for both. Okay. Charge. Charge is conserved. Only electrons move locations. Protons never move locations. Field lines. So field lines point into the negative and out to the positive. And when they're just a single point charge, they are straight lines. They do not bend. They are straight into and straight out of. And they must include arrowheads showing their direction. They only bend when they are near something else. Otherwise, they're straight lines. And they go from the positive to the negative, and they go away from positives. And then for magnetic fields, it goes from north to south, and away from north, yeah. So south acts like a negative charge, and north acts like a positive charge. If I see a question with 20 degrees Celsius, you are thinking the resistivity is stable. That's the only time you're going to see that temperature. Is the amount of resistance across sectional area given? The area is that around, and you can also use the area formula on your reference sheet, the length. And then we have the resistance. Resistivity is different than resistance is the R. Resistivity, that's the P. This is the P right here. Ohm's law. Okay, remember V is the king. He does not like to be on the bottom. He sits on the top. V equals IR. This is in your formula. R equals V over I. V is never on the bottom. V is voltage. It's measured in volts. I is current. It's measured in amps. R is resistance, and it's measured in ohms. Okay, here we have a series circuit. Once we know we see it's a series circuit, we're going to look to this section of the reference table in electricity. We know it's a series because to go through each resistor, I can only make a single loop through each of the resistors. So the current is the same everywhere in there. Total resistance is greater than each individual resistance. So here, my total resistance is 8. The voltage drop across each resistor adds up. So here I've got a drop of 3 volts, and 6 volts across. But when I add them up, I get my 12 volts. Here we've got our parallel circuit. I can make different loops through each one of these resistors. I can go through the 2 ohm resistor. I can go through the other 2 ohm resistor. I can go through the 6 ohm resistor. I also could take out these 2 ohm resistors and this circuit would still work. The total resistance here, though, is less than each individual resistance. The total resistance of this circuit is less than 2 ohms. And the current in each of these loops adds up to the total current here. And each of these gets 12 volts. Okay? So when you're drawing a circuit, if they tell you that they need to draw one battery connected to one light bulb resistor in parallel, and they give you things like how much current and stuff is that, they didn't tell you to label it. Do not do more things than they tell you. Just draw it out. You're going to use the circuit symbols from the reference sheet. So if they gave the battery, you can use either one of this is the battery symbol, this is the resistor symbol, and this is a lamp. You're going to grab those symbols, and then you're just going to draw them out. Because it's parallel, I'm just going to draw them actually parallel to each other. And then you just connect the wires around them. And that's all you would have to do to draw them in parallel. Okay, ways that prove light is a wave. Interference, refraction, diffraction, polarization. Those prove that light is just a wave. The ways that prove the particle theory, the big one is just this photoelectric effect. This photoelectric effect is the important one that proves that light was a particle. Because there's two theories and both work, there is this duality that sometimes light acts like a particle, sometimes light acts like a wave. Both theories are true, and they can be true at the same time when you're talking about reflection. Because like when you're thinking about a particle, you can bounce a wall off of, when you bounce a ball off a wall, it follows the law of reflection. Just like the wave will follow the law of reflection. So there's times when it follows, they can both act like a particle or a wave, and you don't know. But there's times when it acts like a particle, and there's times when it acts like a wave. It matters on the situation. A photon is a tiny particle packet of light, the fundamental building block of an electromagnetic wave. Photoelectric effect proved light was a particle. The E equals HF, that's the formula there. If you have this chart, this slope right here is the Planck's constant, the slope of the line. The frequency just has to be greater than the threshold frequency, but that's a little beyond what we need. So when it comes to energy level diagrams, you need to grab this formula from the reference sheet. It tells you that the energy initial minus the energy final. The energy initial is whatever like level they tell you you're starting at. If the level is a number, then it's the hydrogen chart. If the level is a number, the level is a letter, then it's the mercury chart. And you just got to subtract. But be careful of this. You're going to be subtracting a negative. So you're minusing a negative number. So be careful how you put that in. And then when you want to convert 1 electron volt, when you want to convert it to joules, you just multiply this number, whatever you get, times 1.6 times 10 to the negative 19th, and that converts it to joules. Okay, classification of matter. Hadrons are the protons and the neutrons. Your leptons are your electrons. So when you're over here, this is our neutrons. This is our nucleus. Our nucleus is our strong nuclear force and our weak nuclear force. In here is where the nuclear force is. This is our nucleus. So in the baryons is where we have our protons and our neutrons. And here is where we have our forces that keep everything bonded together. So if we have a proton, we have there are 2 up quarks and a down quark, and a neutron is 2 downs and an up. If I had a meson, I would have a quark and an anti-quark. So I could have a top quark and an anti-charm quark. Okay, so that would be that the anti-charm has a negative 2/3 charge. It has the same E, but just the opposite charge. The only ones that don't have the opposite charge are ones that have 0, like a muon, an anti-muon neutrino is a 0 charge. So an opposite of 0 is 0 still. But yes, so the anti ones just swap the charge around. Okay, things to remember. Conservation of charge. Charges, remember, always conserved. Conservation of energy. Conservation of mass. E equals mc squared combines the idea of energy and mass. So if I have if I combine a proton and an antiproton, I am going to get, they're going to annihilate each other, and that I'm going to get, from that annihilation of mass, I am going to get energy. Okay, so when things are, like if I combine a nucleus, I combine different protons and neutrons, there is this assembly. Some of this is, it should have a certain mass, but that mass doesn't add up, and that's because there's energy lost to binding. And we call that the mass loss to binding energy, the mass defect. So one of the ways to find this mass defect is the energy required to separate atoms in a nucleus is 36 electron volts. The mass equivalent of this energy in universal mass units is this. So we set up using this 1U is equal to 9.31 times 10 to the second mega electron volts. And we're looking for this. So this fraction is equal to 1. And then we're looking to set another 1 equal to 1. When you cross multiply, you get this times this 36 times 1U. 36 times 1 is that. And then you get the question mark times this. So you get 36 divided by times 931 to that. And it ends up being 0.03 something. And that's where you're getting the number for the U value. And the mass, it's just converting this idea that we can't have, mass is conserved, it just has to be converted into something else. I think that's everything. Just study and do that. And just keep practicing problems. Oh, this is how you can do a converting electron volts into joules. You just always want to be setting things up into setting a fraction of 1.